Okay, in previous class, we were seeing advantages of IP. Then also we have started optimization, the need for optimization, right? So here, one more key aspect of need for optimization is IP versions. In previous class, I already told you there are two versions of IP are there, IPv4 and IPv6. Okay. So what is the disadvantage of IPv4? That also I already told you. The IP addresses are all IP addresses are exhausted with the IPv4. So now we have to switch to IPv6. Okay. Then I told you some techniques like translation and tunneling. Okay, by using these two techniques, we can now use both of IPv4 and IPv6 because in nowadays, right now, earlier we started to use IPv4. There was a purely IPv4 era, but now we are starting to use IPv6 also. So since there are all both the type of versions of IP like IPv4 as well as IPv6, we should use these techniques like uh, tunneling and translation. Okay. So next, I also told you cellular provider and technologies based on this. Also, we can select either IPv4 or IPv6. Since 1G, 2G, 3G are supporting only IPv4, they are operated only on IPv4. There we can use only IPv4, but 4G and 5Gs are using either IPv4 or IPv6. So here you have a flexibility to use IPv6. So you have a freedom to use any one of them. Okay. So still the day has not come that we are not using a purely IPv6 still. Right now we are using IPv4 as well as IPv6. So tunneling and translation like techniques are required now. Now let me to move to next point, that is serial communication. Serial communication here, in between a source and destination, or if you consider these source and destination as a client and server. So earlier what happened in serial lines, the serial port was there, serial port of a particular device. That serial port was directly connected to the serial port of a server earlier. But now the service providers stopped this facility providing this service. It means that they are also started to upgrade. Now along with them we also should keep on upgrade. See, service providers started to stop this service. That is nothing but there is no any direct connection. That is usually we call them as a global connection. So earlier we had this facility, global connection, and this facility or service was provided by service providers. So here what actually service providers were giving means, the actually what happened is in between client and server there was only one link, one communication path. So here the source or client device, whatever it may be, so it's that port was a serial port. That serial port was directly connected to the serial port of the destination device. But that connection usually we call it as a global connection. But these service providers stopped to provide this type of services or facilities. Then what is the solution for it now? Now we should communicate with the local connections. That is the solution here. Then what do you mean by local connection? Local connection is nothing but here the serial port of our client device will be not directly connected to the serial port of server. Okay, so this serial port of our client will be first connected to the nearest router, nearest device, nearest neighbor. Okay, and that serial port of that nearest neighbor will be connected to our client's serial port. So our serial port of our client is connected to the serial port of a nearest router first, and from that router to next router or next path or next switch, so many devices will be there in a network. So like this, from one device to one device we are keep on connecting. the serial ports, and then last we will connect the serial port of last router to the serial port of the server. So this is called as a local connection. Okay, so I hope you are understanding what is the concept in this serial communication. Okay, so this what this local router does, it keep on forwarding the packets, IP packets, or it keep on forwarding the traffic over IP up to where? Up to central server for the processing. Is it clear? So serial processing is nothing but earlier we had a direct connection between a serial port of a client to serial port of a server. Now it is not there in our scene. Now we started to use a local connection because service providers stopped to provide the global connection services. So local connection meaning is the serial port of your client device is connected to the serial port of a nearest router, and the serial port of that router is again connected to the serial port of next router. Like this, many intermediate routers are there. Then last we will connect to the serial port of the server, and that server will process that data whatever you are transmitting from client to server. Okay, so now next point is IPv6 adaptation layer. See, many physical layers and the data link layers, particularly for IPv6, if you consider, there are two models I already told you, adaptation and adaptation layer. But here I am talking about adaptation layer. It means that, so if you consider physical layer and data link layer for this IPv6, then even some standardized IoT protocols will support only IPv6 only. They are not supporting IPv4. Then what is the solution now? So most commonly used physical link and data link layers like Ethernet, Wi-Fi, and cellular, so many. This type of they will specify adaptation layer for both the versions like IPv4 and IPv6. So these physical and data link layer are for IPv6 only. But most commonly used nowadays, it is the fact, no, nowadays we are using both IPv4 and IPv6. So these most commonly used physical layer and data link layer will support both IPv4 and IPv6. So here it means that whatever the device is there which is working in the completely in this IPv6 adaptation layer or in the IPv6 network, these all devices must communicate only through the IPv6 subnet only. Okay, so if it is a purely IPv6 network, then definitely they have to communicate through the IPv6 network only. Okay, this is about the adaptation layer. Now we will move to next topic, that is also main and very important topic, optimizing IP for IoT. Optimizing IP for IoT. In the beginning only I told you what we are going to optimize here. We are going to optimize, or we are going to improvise, or we are going to update the internet protocol, which is called as a network layer protocol. And particularly here we are using this IP for which technology? We are using this IP for IoT. So earlier we have used IP for computer networks. So, but here we are basically for mainly we are using this IP for IoT, and this Internet of Things, whatever we are calling in our day-to-day life as a IoT. The main reason for success of this IoT is this internet protocol only. It is also one of the major reasons of success of IoT, because IP is supporting IoT in all ways. Okay, so it is supporting IoT in so many other different ways. And here in IoT, there are some devices are there, what I already discussed, that is constrained nodes or constrained devices, which have some limitations, restrictions, or constraints on them. Okay. And similarly, the collection of these nodes are called as constrained networks, which have some limitations, restrictions, or some constraints. Okay. So these limitations, this type of constrained nodes and constrained networks, they want to update themselves. They want to provide more services. No, they don't want to be in a limitation or some conditions or some constraints or some restrictions. They also want to update. So because of that only, these networks or these devices, they made it compulsory. That is, they mandatorily they made it optimization. They want optimization. And in particularly where we are going to do this optimization in a different layers, not at a whole. The optimization will be in each and every level, each and every layer. Okay. And this optimizations are not only for devices, not only for the networks. These optimizations are for multiple number of protocols also in our IP architecture. Okay, now onwards, whatever the topics I am going to discuss here, these all are nothing but they are optimizations. Okay, so the optimizations which are already present in our market, okay, which are already available in our market, and we are going to see some optimizations which are under development also. Okay, and who are developing these optimizations? Definitely, already I told you one standard body is there which will be keep on regulating our internet. That is Internet Engineering Task Force. Okay, so these optimizations are, some optimizations are available for us now already, or else people are working, or this standard body or this organization is keep on working on some optimizations which are under development. Okay, in next slide, I am going to show you one diagram. So that diagram is nothing but it is a optimization after applying our optimization, how our TCP/IP protocol suite looks like. Because our original TCP/IP protocol suite, it contains some 5 layers, I think: physical layer, data link layer, network layer, and transport layer, and application layer, right? So this is our basic TCP/IP protocol stack. Now, after applying optimization to this TCP/IP protocols suite and how it looks like, and usually we call it as a IoT protocols too, IoT protocol stack. Remember it. Okay, see here. Here in our TCP/IP protocol, we have physical layer, data link layer, network layer, transport layer. On top of this one, application layer is maybe also present, right? So here, if you observe, so here all protocols are there for physical layer, which are wired or wireless, and here are also some technologies or protocols are there. And here also protocol is there for network layer, that is IPv4 or IPv6, and for transport layer also here some protocols are there, TCP or UDP. But one new thing is added here, that is in between this data link layer and network layer, we have added one more sub layer that is called as adaptation layer. Okay, so this is a sub layer which is newly added in between data link layer and network layer. And what this adaptation layer is doing actually here. So after our optimization of TCP/IP protocol, this layer is added now. Okay, this is optimized TCP/IP protocol suite. Okay, in TCP/IP protocol suite, there was no adaptation layer, but this is an optimized TCP/IP protocol suite. So here we have inserted one new sub layer, that is adaptation layer. What is the purpose of this adaptation layer? See, the main purpose of this optimization adaptation layer is you can observe here. Here we consider this physical layer and data link layer as a lower links. And on top of this data link, which layer is there? Network layer is there. And what is the protocol of it? It is either IPv4 or IPv6. I simply call it as IP. Okay, that is Internet Protocol. So this adaptation layer is bridging the gap between this IP and these protocols. Okay, so there was a long gap between this protocol and these protocols, and so this adaptation layer is combining this IP. It is bringing this IP near or closer to these layers, that is lower layers, data link layer and physical layer. That is, it is packaging this IP with data link layer protocols and physical layer protocol. That is the main reason of our purpose of this adaptation layer. Clear? Now, usually you always remember these adaptation layers. Whenever this adaptation word comes, you just remember that there is some limitation is there, there is some conditions are there. Okay, so everything is not proper there. If everything is proper, then that model is called as adaptation model. Okay, but here we are talking about adaptation layer. What it is? See here, the optimization is from this to this. What is this? 6LoWPAN. I already told you 6LoWPAN is a low power wireless personal area network. From this protocol to this protocol, now we are switching. Okay, so like IPv4 to IPv6 we are switching now, like this only. So this is also one sub part or sub form of IPv6. Because of that only it is beginning with the 6. Already we have this 6LoWPAN. Now we want to switch to 6LO. That is nothing but upgradation or updation. That is nothing but optimization. So here, usually we call this protocol or set of devices which are using this protocol. Usually we call them as a working group, 6LOWPA working group. Now we have to shift to the its next successor, or its next version, or its next update. That is a 6LO working group. Okay. So here adaptation layers usually optimize these constrained nodes or constrained networks. Remember, then initial focus of this, or initial aim of basic aim of this 6LOWPA1 PAN was it wanted to optimize the transmission of IPv6 packets over constrained networks. Okay. See, here transmission of which packets? It is IPv6, because already I am using 6LOWPAN protocol, right? So in fact, it will definitely transmit or transfer the data packets which are IPv6 packets only. So the main aim of this protocol was it wants to transmit the IPv6 packets through what? Through constrained networks, through some limited or some conditional networks, or some along with some drawbacks. Okay, that is called as constrained networks, which were using some limited amount of sources. Okay, for example, of these constrained networks are IEEE 802.15.4. This you can consider it as a constrained network. Okay, then once we optimize this constrained networks, then its next versions will come here, like 15.4, 4E, 4G, like this. Okay, but this is a constrained network. Then I'm going to show you the comparison between our already existing TCP IP protocol stack, and we will compare it with our IoT protocol stack. Just remember the difference between IP protocol stack, and now I am going to show you IoT protocol stack. Okay, so here in IoT protocol stack, definitely you will have one adaptation layer. That layer is a 6LOWPAN layer. You can see here left side I am showing you the physical layer, data link layer, network layer, transport layer, application layer protocols. The physical layer protocol, Ethernet physical, Ethernet MAC, and IP, TCP, UDP, ICMP, HTTP, RTP. This is our original IP protocol stack, or you can call it as a TCP IP protocol stack also. But here, once you observe this right side diagram, you can see here this physical protocol is just, it is instead of Ethernet, here we are using IEEE 802.15.4 physical layer or physical protocol, and the data link layer is also same. And here you can observe here we have inserted this adaptation layer in between network layer and the data link layer. We have inserted this adaptation layer, which is a LOWPAN. Then IPv6 is here, and UDP and ICMP transport layer protocols, and then as it is application protocols. The main difference is here we have inserted this adaptation layer in between network layer and data link layer, right? So I think you understood the comparison between our original TCP IP protocol and our IoT protocol stack. Okay, then now we will move to that is a header compression. That is, it means that this 6LOWPAN is there. No, it has some headers, and you can call it as a header stacks. Here, three types of headers we have, one above the other. So because of that only, we will call it as a header stack. Okay. So what is the meaning of this header? Okay. See, in every data frame, you may be having two main units here, two main parts. One is a header unit and one more is a payload unit or a data unit. The data unit or payload unit will be containing your actual message, what you want to send to the destination, your actual data it is. Okay. So here header is there. No, this header unit will be containing the information about your data, or information about your entire data frame, like a source of source destination, source address, destination address, length of the frame. Okay, so many things. That type of information will be present in a header. And in between this header and this payload, now we are going to insert some other fields like subheaders. Usually I call them as subheaders, like IPv6 header compression. Compression is one process. If you want to do this function in your transmission, then you can insert this header here. Okay, and in addition to this compression, one more function is there, that is fragmentation of a header. In addition to these two, one more third operation is there, or function is there, that is mesh addressing header. So in between this header and this payload, you may be required to do these three functions: compression, fragmentation, and mesh addressing. Okay, so just remember the flow of these things. So here, if you want to do only compression header you add here. Okay, if you want to do two processes, fragmentation as well as compression, then fragmentation will be first, then compression will become later in your data format. Okay, frame. Then mesh addressing will first come, then fragmentation, then compression. Just remember here, fragmentation is there, fragmentation header. Okay, after fragmentation header only compression will come here. Okay, header compression will come. Just remember this one, because in next slide I need this. Now let us see one by one how to do this header compression, how to do this fragmentation, how to do this mesh addressing. Okay, see, in header compression, what it is, whenever we are sending a data to the receiver, so if the data is a huge amount of data, then we have to compress it and we have to send it, right? So the same technology we are using here. The one best example I would like to tell you, to understand this concept very easily. Suppose in your family you have four members, and all of you four are going to your workplaces in every morning, and you will return to your house in different times. So all four of you have your commonly used one key of your house. Okay, so that you can come at any time and you can have a rest at your home after your work. But at night, suppose you all are going to a dinner or any some reception or any some family function, right? At that time, usually what happens, the children will not bother about carrying their keys usually. Okay, so because they know very well that their parents will carry the key. Okay, so here unnecessarily all four members are not required to carry the key. Only the parent or the head of the family uh, can carry the key, since all of you are going to the same destination. Are you understanding? The same concept is used here also. Unnecessary data, whatever it was there, which was commonly shared between among all these nodes, so that data was removed or eliminated from our data frame. Then the header, the entire data size is reduced. Okay, so let us see how we can do it. See here, two diagrams are there, top and bottom. In the top diagram, this is showing a frame, a data frame of length 127 byte. The total length of this frame is 127 byte, but if you observe, you are getting only 53 bytes for your actual data. That is 53 bytes of payload. Okay, then what about the other remaining huge amount of data? It is occupied by the huge amount of storage is occupied by the 6LOPAN header, which is occupied 1 byte, and 40 bytes of data storage is occupied by IPv6 header, and 8 byte is occupied by UDP header. Now, this is without header compression. This is when it is before compression, before header compression. Okay, so after compression, how your frame looks like, you can see here. See here, one by one we are compressing here. Here 1 byte of this 6LOWPAN header was there. No, we have compressed it to 2B, 2 bytes. So you are telling that compressing, but here it is increased by 1 byte. No, so how it is compressed? You can observe here carefully. It is a 6LOWPAN header. It is as it is. It is not actually compressed. It is 1 byte only. Okay, it is originally 1 byte and it is remaining like that only. But what we have compressed here actually, 40 bytes of IPv6 header was there. No, this 40 bytes of header of IPv6 is compressed to 1 byte. Then that 1 byte is also added to this field only. So both together, those are two separate fields, I combined them and I am calling it as a 2 bytes of a 6LWPAN header with compressed IPv6 header. IPv6 header is compressed to 1 byte now. So how many bytes we saved here? 39 bytes we saved. right? So once you come to UDP header, here also it was originally 8 bytes, but here we are reducing it to 4 bytes. Almost half we reduced, half storage we reduced, right? So here 39 bytes we saved, and here we are saving 4 bytes, almost 44 bytes we saved here. Then if you observe, you are getting more than 53, double of this 53 bytes of payload in our compressed data frame. That is 108 byte payload you are getting. Where is 53 and where is 108? You just remember, right? This is the beauty of a header compression. Header we are compressed here. Okay. Next, fragmentation. So fragmentation is nothing but dividing the data into small parts. And here also in this field, we are using 3 subfields. They are datagram size, datagram tag, and datagram offset. What is this datagram size? Its name itself is telling that it is indicating the size of the entire data frame or datagram. Okay. So total size of that unfragmented payload. It means still fragmentation is not done. Okay. So the total size of unfragmented payload. Then datagram tag, it says us how many number of fragments are there after fragmentation, how many number of fragments are there. Then datagram offset is nothing but it is just like our array index, which starts from 0. Okay. So whenever you are putting the datagram, it exactly access that datagram because of this offset only. Okay. So here, remember, for suppose there are some n number of fragments are there, the first fragment always will be addressed as 0. It will not be having any offset. So you can save the storage here also for the first fragment. Okay. So we will see here, this is the 6 yellow WPA fragmentation header it is. So this is originally header and this is FCS something is there. And we are focusing only about this white portion. This white portion is nothing but it is a fragmentation header, right? So this fragmentation header is again divided into 4 fields here. So this first field is 1 byte, and what it is going to tell us. The 1 byte is nothing but 8 bits, 8 zeros and ones here, right? So what this 8 zeros and ones are telling us, they are telling us, so after this field, the remaining 3 fields, whatever they will come here, okay? So after this first field, the second field, third field, and fourth field, the remaining 3 fields are also belonging to fragmentation header only. So this is already fragmentation header, right? So fragmentation field it is. The next 3 fields are also related to fragmentation header only. They are not compression, header compression. That information will be given by this fragmentation header. Sir, then where is that compression header? Header compression field. It is here, somewhat here. Okay. So that is not shown in this diagram. So this first field tells us the next consecutive fields are related to fragmentation only. Then 1 byte of this datagram size and 2 bytes of datagram tag, and here we will get totally how many number of datagrams or fragments are there, and last 1 byte of offset is there, which is playing very important role. So this datagram offset is not required for the first fragment. Okay. So if it is not required for the first fragment, then what will be the total length of this fragment header? It will be only 2 bytes plus 1 byte plus 1 byte. That is 4 bytes, only this much. Okay, this is not required for a first fragment. So first fragment's length will be only always 4 bytes. Then what about the length of second, third, fourth, fifth, and so on, that data frames? That will be 1, right? Then the total size of that fragmentation header will be 5 bytes. Clear? So this is about the fragmentation header, right? So now we will go to next operation, that is mesh addressing. Mesh addressing. See, what is this mesh addressing? It means that, whenever we have a source and one destination, and we want to transmit a data from source and source to destination, they are not the only 2 endpoints in our network. In between these source and destination, there are so many intermediate devices, links, routers, switches, so many other things are there, right? So usually we call these all intermediate devices as a hops. So if we want to understand it better, let me to explain it with one beautiful example. Suppose if you want to travel from Belgaum to Kolhapur, okay, so let us count the number of hops in between this path. So once your Belgaum is a source and you have departed from the Belgaum, once you reach the Sankeshwar, that road in between Belgaum to Sankeshwar is considered as one hop, and the road in between from Sankeshwar to Nipani is considered as one hop, and the road in between the Nipani and Kolhapur is considered as one hop. So totally how many number of hops are there in between Belgaum and Kolhapur now? 3 hops are there. And however you are keep on traveling, for every time whenever you are visiting a node, that hop count will be keep on decrementing. It is just like a countdown when we launch the rocket, like 10, 9, 8, 7, 6, like that, up to 0. So once you reach the destination, your hop count will be 0. Then you should understand that I have reached my destination and there is no more of forwarding, isn't it? So same thing is here also. Here for mesh addressing, so we want to forward the packet through multiple number of hops. And here again we are going to use some fields like hop limit, source address, and destination address. Okay, so every time whenever you forward the packet, you will decrement the hop count by 1. Okay, once the hop count will become 0, then you will understand that the no longer of forwarding the packets. There is no any packet to forward. Okay, so let me just show you that mesh addressing header. Here 2 bytes of source address is there, 2 bytes of destination address is there, and 1 byte of addressing header including hop count. This first field will be keep on storing the hop count. Okay, so totally how many number of bytes are used for addressing here? 5 bytes. Yeah, now these all things are there in our mesh, this one. And here usually we use most important options here. 2 important options are here in our mesh addressing. That subtask is called as mesh under. Okay, and one more option is a mesh over, or you can also call it as root over. What it is, mesh under and mesh over. Mesh under will be concentrating on only handling the packets, that's all. And sir, why it should be handle that packets? Because handling the packets in the sense that it is handling the routing of those packets. It is concentrating on how I have to forward this packet to the next router. It is nothing but mesh under is nothing but it is providing some routing table information, so routing algorithms. Okay, then mesh over, what it is going to do? So it is going to utilize that routing information or routing table information for forwarding that packet to the destination. Okay, so these 2 are very important options in our mesh addressing. So till now just you are focusing and you are telling only about 6 LOWPAN, but still now you have not told anything about 6 LO, right? We have to switch from 6 LOWPAN to 6 LO now, right? So here usually the most important concentration or aim of this 6 LO is it want to provide the connectivity. Okay, it want to provide the connectivity of or over constrained node networks. So main concentration of this 6 LO was to connect the constrained networks so that it can transmit the IPv6 packets. Okay, so here earlier what it was done, 6 LO WPA1 was working only with the optimizations of IEEE 802.15.4 LLMs. It means that it is a low power and lossy networks, and standardizing the IPv6 over link layer technologies still required. Since it was focusing only on optimizations of this one, low power and lossy networks, still standardization of IPv6 is required now, because nowadays the world is almost within few years we will start to use purely IPv6. So now still some standardization is required for link layer technologies. So for that only we started to use 6 LO working group. Now it is called as IPv6 over networks of resource constrained nodes. And what is the main purpose of this IPv6 over constrained resource network nodes, constrained nodes, or what is the purpose of this 6 LO? to provide the connectivity again over the standard constrained node networks, but with purely IPv6. Okay, so this is about the transformation from 6L OWPA into 6LO, and very important, you may be asked in your exam. Next one is 6TISCH. Just I take just 2 or 3 minutes break. I think within 2 minutes this meeting will end, and hardly one or two slides are there. One small topic is there. Then I complete it in next session immediately. After 2 minutes, you join it. Join the same link. Okay, and again I take another some 10 or 15 minutes class. Then I wind up today's sessions. Okay, so please guys, you rejoin after 2 minutes.